Hello everyone. Today we're going to be looking at inscribed angles of a circle. So an inscribed angle is any angle that the vertice is on the circle itself and the two endpoints are also on the circle. So as you can see, this angle PQR is an inscribed angle. This is different from a central angle of a circle, which, as a refresher, let's say I have a circle like this. Here's the center, and here's a central angle. And what we know about central angles already is that if the arc it's intercepting is like, all right, let's say it's 80 degrees, the central angle is also 80 degrees. But inscribed angles behave a lot differently, and we'll see exactly why in just a second. So we're first going to tackle this problem right here, where we have a circle with points A, B, and C on this circle, the circle with center O. The arc AC has a measure of 80 degrees, and the arc BC has a measure of 64 degrees. So we want to find out what the measure of angle ABC is. The angle located right here, our inscribed angle. So parts A, B, and C are going to help guide us to get towards that solution. So part A says to draw the segments OA, OB, and OC. First part. So I'm going to get my little tool, draw OA, OB, and OC. Now, what's important about those three segments that we have just drawn is that they are all the radii of our circle, because they are all drawn from the center to each point on the circle. And we know that all the radii of a circle have the same length. So OA is congruent to OC, which is also congruent to OB. And this should also sort of, something should pop out at you right now, since when we created all these lines, we got a bunch of triangles, and triangles with congruent sides. And whenever I have these congruent sides in triangles, that means they're either isosceles or equilateral. Well, if we look at something like triangle AOB, where two sides are congruent, that means it's an isosceles triangle. And because it's an isosceles triangle, it means these two base angles right here and right here are going to be exactly the same. And we can also see triangle OBC is isosceles because OB and OC are the same. So that means their base angles are going to be equal as well. So this angle here and this angle that takes up the two smaller ones is going to be the same. They're equal, which is going to help us find out the measures of angle AOC and COB. So let's start by finding angle AOC. So angle AOC, well, that's this angle right here. That is a central angle. So we know central angles have the same measures of their arcs that they're intercepting. So since the arc AC is 80 degrees, this central angle must be 80 degrees as well. Angle COB is another central angle, an angle where the vertex is at the center of the circle, that's intercepting an arc BC. So that means the angle has the same measure of 64 degrees. Okay, so that's everything for part A. We're done. For part B, we have to find angle OBC. So that's this larger angle right over there. Well, like I stated earlier, since OBC, the triangle, is isosceles, the angle OBC is congruent to the angle OCB. And because we know that remaining angle is 64 degrees, we can use the fact that all three angles of a triangle add up to 180 to figure out the measure of the angle we're looking for, OBC. So I'm going to say, okay, we need to do 180 is equal to 64 degrees. And, let's just call these angle measures like X, X. Well, then 180 is equal to 64 degrees plus X degrees plus X degrees. So we can combine our like terms. 180 is equal to 64 plus 2x. Subtract 64 on both sides. So that gets us 180 minus 64. That would be 116 degrees. And that's equal to 2x. And 116 divided by 2, that is going to get us 58. So x is equal to 58 degrees. That's a weird looking equal sign. Hold on 1 second. Okay. And again, that x represents our angle OBC. So angle OBC is 58 degrees. All right, now we want to find out what angle OBA is. Well, it's basically the same exact idea we were just using. Okay, we got that triangle AOB is isosceles, which means those two angles, the base angles, are the same, the ones with the single tick mark. So let's call that like Y, like a Y degree angle. And that top angle, the vertex angle, would be equal to 80 plus 64, which gives us 144 degrees for that angle AOB. So to find the remaining measure, or the angle Y, we know that 180 is equal to 144 plus angle Y plus angle Y. So I'm just going to shorten it up, plus 2Y. All right, so then we will subtract 144 from both sides of the equation. 180 minus 144 is 36. That's going to be equal to 2y. Divide by 2 on both sides, and that angle y is going to be equal to 18. Okay, so I'm going to clean up the picture a bit since now we, have a better idea what's going on. Angle OBA is equal to 18 degrees. All right, let's clean up this picture a bit. Get rid of some of the fluff we don't really need anymore. Okay, so we know this angle right here is 18 degrees, and the entire angle itself, the entire angle is 58 degrees. So finally we can figure out what is angle ABC. Well, that's the, second part of our angle OBC. So all we have to do is take 58, subtract 18 from it, and we are left with 40 degrees as our answer. So angle ABC is equal to 40 degrees. Okay, wonderful. So why do we always have to go through all that work every time to find an inscribed angle? Well, not really, because what happens if, let's say, I'm going to kind of clear some of this stuff out. Let's look at the relation that our answer has with the problem, like how it started. So we started with the fact that, let's get rid of all this, because the important part is now we know that our inscribed angle was 40 degrees. And I'm even going to get rid of those extra lines I added, and we'll go back to basically how the problem looked originally. So we had this inscribed angle ABC. We wanted to find out what that was. And we were given that this arc AC was 80 degrees. And we found through all that work that the inscribed angle is 40 degrees, which is half of the measure of that arc, which gets us thinking, hey, is that always going to work out? Is that how it's going to work out every single time? Well, let's see. So this is going to be our, investigation on whether this is always going to be true. We have this inscribed angle XYZ, a circle with center O, and we're trying to show that this angle XYZ is equal to half of the arc XZ, half of that arc it's intercepting. So to start us out, we're again going to draw some lines from the center of the circle to our 3 points of interest. So OX, OY, and OZ. Should also note that all these lengths have to be the same because they're the radii of the circle. And we should also note, hey, just like last time, we're going to get a bunch of congruent angles because we get a bunch of isosceles triangles from that. So I can say confidently all these angles, or I mean not all these, but angle OXY and OYX have to be the same because it's an isosceles triangle, and angle OZY and OYZ are the same for the same reason. So if we let the angle OXY equal like lowercase x, then I know that this angle OYX is also that same measure, lowercase x. And if we say that angle OZY is lowercase z, then I know OYZ is also lowercase z. So, all right, now we have something to kind of start us out. So for part B, we want to find the measures of XOY, YOZ, and XOZ in terms of x and z, lowercase x and z. So let's start with the angle XOY. Well, angle XOY is an angle of a triangle, and we have an expression for the other two angles. They're just our lowercase x. We know all three angles of a triangle add up to 180. So what I can say is something like this. 180 is equal to angle XOY plus angle x plus angle x, which is basically just plus 2x. And again, I got the x here, plus angle XOY. That's how I'm forming that equation. And if I simply subtract 2x on both sides of this equation, we get 180 minus 2x is equal to angle XOY. So now we have an expression for our angle XOY in terms of x. We know that it's 180 minus 2x minus 2x. A little funky looking, but whatever. Okay, now we want to find an expression for angle YOZ. Well, same process, right? YOZ is this angle right here, the third angle of our isosceles triangle ZOY. We know the other two angles are in terms of lowercase z. So same thing's going to happen. So, you know it's going to happen. You can write it the full equation out like I did in the first part, but I'm just going to go ahead and say, okay, angle ZOY is equal to 180 minus 2z. By the same process that got us the values for angle XOY. Same exact process. Okay, so now we have an expression for that angle. 180 minus 2z. It's a little cramped writing everything in there, but that's what our angle ZOY is. So now we want to find out an expression for XOZ, which is this angle right here, this one there. How can we express that angle in terms of x and z? Well, if we combine all three of those angles, right, like this angle, and this angle, well, that is a complete rotation, which means that would altogether have a measure of 360 degrees. So we can set up an equation just like that. 360 degrees is equal to angle XOY, which we know is 180 minus 2x, plus angle ZOY, which is 180 minus 2z, plus the angle we're trying to get an expression for, that angle XOZ. Okay, from here, we can hopefully see, okay, 180 and 180 is 360. And we can combine that together, 360 minus 2x minus 2z plus angle XOZ. All that is equal to 360. Now, if we subtract 360 on both sides, two of the 360s cancel out. We'll actually get 0 is equal to negative 2x minus 2z plus angle XOZ. And then finally, let's add 2x and 2z over on both sides of the equation. We would get 2x plus 2z is equal to angle XOZ. And that's what we're looking for. XOZ is equal to 2x plus 2z. So, okay, this angle XOZ is 2x plus 2z. And note, okay, that angle XOZ is a central angle, which means since it's a central angle, it has the same measure of the arc it's intercepting. The arc that angle XOZ is intercepting is the arc XZ. This one right here. So that means our arc XZ has that same measure, 2x plus 2z. Well, if we look, again, if I get rid of all this work we've done because it's cluttering up everything, let's erase some of this stuff and just look at the inscribed angle that we had. And let's get rid of some, I know this is fine. So that inscribed angle we started with, angle XYZ, this one right here. Well, we could see that has a value of x plus z. And through all our work, we found that the arc has a measure of 2x plus 2z, meaning that the arc is twice as big as that inscribed angle that we started with in the beginning of the problem. And that is basically our proof, because if this arc is twice the length of the inscribed angle, then the inscribed angle is worth half as much as that arc xz, which is the very thing we were trying to show, that our inscribed angle xyz is equal to the arc xz divided by 2. So this gets us our nice important theorem with inscribed angles, where the measure of an inscribed angle is equal to 1/2 the measure of the arc it is intercepting. So if in this case we have this angle PQR, our inscribed angle, it's equal to half of that arc PR that it's intercepting. Alright, hopefully that makes sense, and I will see you in the future for some more videos on circles.